Okay, a pebble is dropped into a pond, causing ripples in the form of concentric circles. You've all thrown rocks in the water before, and once you drop it in the water, you just get these multiple rings, that disperse going out from the center. The radius r of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So you have these different rates in which the area is changing at different times. So we're wanting to know exactly what would that be when you finally get a radius of 4 feet for these concentric, or for one of these concentric circles. All right, so again, write down what you're given. What have you got to find? Okay, and this is where things are not just, quite as obvious as they were a while ago. Now, a rate of change. You know that you're given a rate of change anytime that you have something per something, okay? So I know that this 1 foot per second is a rate. And if you notice, it's the rate in which the radius is increasing, okay? So I would definitely suggest that you use variables that relate to the problem. Since you're talking about the rate of change of the radius over time, then you refer to that as dr dt. It's not just r because it's a rate, so therefore it has to be the dr dt, and that would be 1 foot per second. Okay. Now the other piece of information that I have is that the radius is 4. And again, the radius is not 4 all of the time. It's just at that particular moment in time, when that radius finally reaches 4 feet, what is the rate of change of the area at that particular time? Okay, so now what have we got to find? Okay, so at what rate, so anytime that something's a rate, you're going to be using this type of notation, d something dt. Okay, of course the bottom's always going to be dt because it's all this is done with respect to time. So at what rate is the area changing? So since we're talking about area, then I'm going to call it dA dt. And I would use, you can use lowercase a if you want to, but use uppercase A. That's what you typically do when you're talking about area. Okay, so there's my given, there's my find. So now I've got to get an equation. Well, you're talking about the area of a circle, so your equation is going to have to be the formula for the area of a circle. So A equals pi r squared. Okay, so now you're ready to do your implicit differentiation. So you're taking the derivative of A, which would just be 1, but with respect to time, so that would have to be dA dt. Now, pi is just a number, okay, so that's just a constant multiple. So we're going to use our power rule on our r squared. So that would have to be 2 times r. Of course, to 1 less power, that would drop to the first power, but you're taking the derivative of an r with respect to time. Okay, so now let's substitute in what we know. Of course, we're trying to find dA dt, so that's already on one side by itself for us. Okay, so we're wanting this rate of change specifically when your radius reaches 4. And the radius is changing at a rate of 1 foot per second. Now we'll worry about putting on the units on our answer in just a minute, so just substitute in your 1. So dA dt, that would, as far as a exact answer, you just have to say 8 pi. Now you're talking about the rate of change of the area, so that would have to be feet squared per second, but it is a rate of change. So just like I told you, rate of change is always, like here you have something per something. Down here this is going to be something per something, but since it's area, you've got to do it with square units. So that would be your exact answer. I'm not for sure what the answer like in the back of the book. If they round it off, then just put that in your calculator and see if you've got the correct answer. Okay, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Okay, so given. Okay, so we have, see right here's a per, so we have 4.5 cubic feet per minute. So that would be a given rate. Of course, that would be the volume because it's in cubic units. So I'm going to call this dV dt. So dV dt would be equal to 4.5 cubic feet per minute. Okay. And we're looking at this rate of change when the radius finally reaches 2 feet. And what am I trying to find? I'm trying to find the rate of change of the radius. So that would be dr dt. So rate of change of the radius, so r. All right, so we're dealing with a spherical balloon. So in other words, we're dealing with a sphere, three-dimensional object, therefore its volume. So the equation that you need is going to be your volume for a sphere. Okay, so you may run across, some volume formulas that you may not remember off the top of your head. If you've got that textbook handy, it actually has some formulas like in the very back cover, but you can always Google, anything that it is that you're needing. But here's your formula. Okay, so you've got to do your implicit differentiation. Again, do not substitute anything in, okay? Now, I mentioned a while ago that I would say something about, sometimes you can plug information in, and I'll get to an example a little bit later, so I can probably compare it a little bit better. But the radius is something that's changing. Like as you're filling this balloon full of more air, it's getting bigger and bigger and bigger and bigger, which then means the radius is getting bigger and bigger and bigger and bigger. So anything that is changing, that continues to change over a period of time, based on whatever the situation is that's being described, those values cannot be substituted in until after you've done the implicit differentiation. One example of something that you actually could plug in ahead of time, like as soon as you write your formula down, you could actually go ahead and plug in, is like if you have the shape of a cylinder. The shape of a cylinder is like your paper towel, the cardboard inside your paper towel roll, It doesn't matter what's being done with the shape of a cylinder, the radius of a cylinder is never going to change. It's straight up and straight down. It doesn't expand out, like a balloon does as it gets bigger. So if it's something that doesn't ever change, a dimension that never changes, you can plug it in here before you do the differentiation, and there's going to again be some cases where we're going to do that, but your radius of your figure changes, so you can't do that. Okay, so taking the derivative of v with respect to time. Now 4/3 pi, that's just a constant multiple, remember. So now you're going to take the derivative of r cubed using your power rule, so that would be 3 times r squared dr dt. Okay, so let's substitute in what we know. We know that the rate of change of our volume is 4.5. And radius, we're looking at this when radius reaches 2. And of course, we're trying to find dr dt, so I don't have anything there to plug in. Okay. Of course, this is understood to be over 1, this is understood to be over 1. So like I can do the 4 times the pi times the 3 times the 4 squared. So let's just go ahead and multiply all of that. That's going to give me 48. Let's see, 4 times 3 is 12. Yeah, so that would be 48 pi divided by 3 dr dt. Okay, so then if you want dr dt by itself, let's multiply both sides by the reciprocal. And we'll just go ahead here and get us a decimal approximation. Of course, all of this cancels, giving me my dr dt by itself. So 3 times 4.5. And then I need to divide that by 48 pi. Now be careful, like when you're putting in this 48 pi, you would need to have your denominator in parentheses. Hang on, I hit the button wrong, so give me just a second. Okay, so I'll keep 2 decimal places. So this would be about 0.09 if you keep 2 decimal places. Now, as far as your units on this one, of course, you're just talking about radius. This is just a linear measurement. So if this is in cubic feet, then this would just be feet. But of course, it's a rate, so it's feet per minute. So this would be your answer.